Hi, so my name is Silviu Calinoiu, and I'm the technical lead for the Cloud Data Flow for Python. And to me is also Eric Anderson, who is the program manager for the team. Before I start, I'm just curious, can I have a show of hands? How many people heard of Cloud Data Flow? All right. I was asking how many people have heard of Cloud Data Flow. Okay. So in the next 30 minutes, we're just going to build from scratch a typical ETL pipeline, processing pipeline that will take some text files in JSON format and output some aggregated data to a BigQuery table. That's like a typical thing that you do with these kind of systems. So before I start, I have 2 slides that are written by some colleagues of mine. I'm going to keep it short, but just to kind of give you a background of what is Cloud Data Flow and how we arrived there. So a long time ago in 2004, it was MapReduce. There was a seminal paper from Google that started 2 divergent efforts. So inside Google, for many years, they continued to innovate. But outside, all you have seen is just a bunch of PDFs for various systems, Flume Java, Millwheel, Dremel, and a bunch of other things. Whereas outside, the open source community continued to innovate for all these years, and they created their own ecosystem of tools. There was a little bit of cross-reference through the papers published in both ways. But other than that, Google never actually had a public system that people can play with. In 2014, we announced Google Cloud Data Flow, which is it's a combination of something called Flume Java. It's an internal system for describing batch computations by describing a processing graph of custom transforms. This is combined also with a system called Millwheel, which is used for streaming processing. So that's actually one of the major advancements with Cloud Data Flow. It's this combination of a unified API both for batch and stream processing. And quite recently, in January 2016, the Cloud Data Flow team, together with some industry partners, they contributed the model to the Apache Software Foundation in a incubating project that's called Apache Beam. So I'm saying all this stuff because you will hear about Apache Beam, Cloud Data Flow. So this is kind of the history of it. So at this point, we like to call it the Apache Beam model of processing, model for processing data, both batch and streaming. And Cloud Data Flow is really just a service offer for Google to run such a pipeline in our own cloud. But the model is called Apache Beam now. So as I said before, I'm not going to delve more on this. One thing I forgot to mention here. So Cloud Data Flow shipped with a Java SDK API. So basically, you will be able to describe all these processing graphs in Java. So what I'm going to talk now is a much more recent project where we offer the same computation model in Python. So that's something new that we just a week ago we launched our alpha version. So as I said, you can, with the Java one, you can do both batch and streaming. So you can have bounded sources of data, or you can have unbounded. You basically can process forever incoming data. In Python right now, we support only batch. So we're still working on streaming, so it's going to come on. But right now, we support only batch, and this is what I'm going to show you today. So I just want to, I want you to remember 4 concepts that are going to show up in the coding. I'm going to call them out then. But The four are pipelines. So this is the thing where you put your processing graph. This is the object where you put you construct your processing graph. You associate with it a runner. So runner can be something that will run the graph that you just described locally on your local machine, or it could be something that will run in a cluster, in a cloud. For Java, for instance, there are actually runners. There's a Flink runner and a Spark runner, which are these equivalent systems from the open source community for describing these kind of computations, where basically the same graph, so you use the Apache Beam model to describe your computation, and then with a Flink runner, that computation will be submitted to a Flink cluster and run there. In Python, we don't support that. So right now, we support only a direct runner, which runs locally, and Google Cloud Runner, which will run the computation in a Google cluster. So pipeline and runner. The other two concepts are p-collection and p-transform. So think of p-collection as a very, very large list. This is what flows between through the edges of a processing graph. So if you want conceptually, it's a little bit more complicated, but conceptually think of a directed acyclic graph where the nodes are transforms that do various computations on the incoming data and output some other data. And through the edges flow these p-collections. So you will see that basically the graph is about chaining these p-transforms and doing something with the p-collections. And in terms of p-transforms, really there are four important types. So it's first the in nodes and out nodes, so a read transform and a write transform that allow you to insert or output data from the processing graph. And then you have a parallel do, which is something custom that you do for each incoming element of a p-collection. And group by key, which is something that will it expects as input a p-collection that contains key value pairs, and you will group the values by keys. It's a pretty, so if you think of it, parallel do is the map part of MapReduce, and group by key is the sort of the reduce part of MapReduce. But the thing with all these systems, modern systems, so Dataflow, but also Flink and Spark, is that it's not just one MapReduce. You have a whole bunch of MapReduces chained together in this graph. So, so one more thing before we start coding. So the project is on GitHub. You can check it out. There is a form here that will allow you to sign up for our alpha program if you want. You don't need to sign up if you just want to play with it locally. But if you want to run against the Google cluster, you need to sign up. And right now, it's kind of invite only. So we need to whitelist people before they run against the cluster. The other thing to mention is that we're also moving to Apache Beam. So right now, we are in a separate GitHub repository. But eventually, we are going to be also part of the Beam incubating project. And as I said, we don't have streaming yet. And the other thing is that the Java version has a plethora of sources and sinks. So you can read from all sorts of things. In Python right now, we can read and write only to Google Cloud storage files or local files and BigQuery tables. By the way, I'm just curious, how many people know what BigQuery is? Okay, so many more people. So BigQuery is the warehousing solution from Google. It's a pretty awesome no-knobs warehousing solution. Okay. So we're going to start doing stuff now. So the first thing I recommend is whenever you play with something new, use a virtual environment, so for your sanity. Because you're going to install all sorts of packages and you don't want to install them in a global environment. All right, so as I said, actually, let me see. So this is the GitHub repository. I'm just going to install the latest release. 021. There is one more step actually that I'm a little bit lying here. There's one more step that you need to do that's already installed on this. You need to install a bunch of Google Cloud tools, but it's all described in the README that's in GitHub if you want to play with it. All right, so we have a clean slate here. Now it's clean. So the first thing we're gonna basically describe a computation. We're going to have some toy files locally, and then we're going to have somewhat bigger files towards the end where we're going to run we're going to run in the Google cluster. So the first thing you do is you just import the package. So this is kind of the standard way of doing it. It would be nice if this is this tent would be stable. All right. So remember the concept. So the first thing is we create a pipeline object because that's where we're going to put all our computational graph. And for now, we're going to use a direct pipeline runner, which is basically we're going to run this locally. Later, we're going to use another one. So the first thing, we're going to read some data. So I'm just going to write it, and then I'm going to talk about it. So basically, we are applying a read transform that will read from a text file source, and in this case, it's just one file that I have it here locally. So is this data in just has this a bunch of JSON records line by line. All right, so what I said here is that, okay, apply this read transform and create this PC variable. This is a P collection. The P collection is going to contain, each element is going to be one line from the file. So the line, the file could be as very big. It could be actually a collection of files. It doesn't matter. Conceptually, what you get at the output is a P collection with all these lines together. And now we're going to do something very simple. We're going to write the P collection out. Right. So what I'm doing here, these 3 lines, I build a processing graph. Very simple one. In fact, it's probably the most ridiculously complicating file copy that you can ever imagine. But you know, it's going to get more interesting. So the only thing that it's missing, you need to actually initiate the runner. So you need to run the pipeline. So that's all you have to do. All right. So now I got this stuff in the output file. Fine. So now let's try to do a projection here. So I have these JSON records with a bunch of fields. I want to filter to get only the product ID and price. Because what I want in the end, I want an aggregation per product ID, how much stuff I sold, right? So the first thing I want to filter only product ID and price. So first of all, there's no need to split it line by line. Oh, by the way, one thing I should mention, we call this the pipe operator. In general, we try to make this API very Pythonic, so we obsessed a lot about it. the pipe operator was something that we were very proud of, but when we presented to people, it's split 50-50 between people considering it Pythonic and other people being nonplussed by it. So, but for now, we stuck with it. I think it's a good metaphor. It reminds you of the pipe operator in when you do bash commands. So anyway, what I wanted to say is that you don't have to create all these temporary variables. You can just write the whole thing in one pop like this. So now I want to, for each element, I want to filter only the fields that I want. So basically, I'm going to apply a parallel do. So in Python Dataflow, there are 3 types of parallel do's. They're basically all do the same thing, but there are small variations. So a map is one that maps an incoming element one-to-one to an output element. So it's one-to-one. There is a flat map that will map one element to 0 or more elements. And there is a par do, which takes a generalized form. You need to define a subclass of a doFn class, and it takes a bunch of extra options. But with map and flat map, you just specify lambda functions or normal Python functions. So in this case, let's say I have a parse record function that I need to define. So let's see, parse record. So this takes one element. If you look at the pipeline, actually what's going to get, it's going to be called for each line of the input file, right? So let's say I want to get a record out of it, and then I want to return the what's called the product ID and the price. Okay. So let's see what we got here. That's interesting. Okay, so this is the, I was missing an S. So load actually reads from, I don't know, load S reads from a string, load reads from a file or something. Yeah, so anyway, this is gonna, okay, so now I got the data filtered. All right, so the next thing that I want to do is I want to group this by, so sorry, I'm kind of glossing over, I don't know exactly the level of Python knowledge here, but basically what I'm returning here is a 2-tuple in this line 6. This is how you represent key value pairs in Python Dataflow. So whenever you want a key value pair, you return a 2-tuple. And key value pairs are very, very common because whenever you want to do grouping, that's what you need. You need key value pairs. So in this case, we're going to use one of the grouping transforms, not group by key, something called combine per key. So imagine combine per key will do something like this. So as an input, you get these key value pairs, right? And lots of them. And this combine per key is going to group all the values for each key. So each key is going to have basically a list of values. And then it's going to apply a combining function to all the values associated with the key. So basically what you get key sum of the values associated with the key, something like that, which is exactly what I want because I want to add up all the sales for a particular product ID. All right, so now I got my final result. I want to show you something else that's interesting before we start doing the BigQuery part. So as you notice, at this point, we're outputting everything into a file, local file. I want to show you how you can use here a Flatmap. So the difference between map and Flatmap is that map is one-to-one, and Flatmap return is a mapping from one to an iterable of values, 0 or more. So if I say Flatmap here, now this becomes incorrect, the function, the way it's written. And the reason it's incorrect is what this returns a two-tuple. Well, it so happens that the two-tuple is an iterable, which means that this infrastructure, the whole framework is going to consider that the two values associated with an input are going to be product ID, then price, which is not what you want. You want the key value, both of them grouped together. And so this is the kind of stuff that Python is very hard compared to Java. So in Java, there's this strong type system. So you will not be able to make this kind of subtle mistakes. So in Python, because we don't want this to happen, so the reason, I mean, obviously people program in Python and they get used, they kind of develop defense mechanisms to deal with this kind of stuff. But in this case, it could be even costly. I mean, it could be that, for instance, you don't run it locally or you send it to the cloud, you're going to pay $1,000 to discover that you missed a type. Because in the cloud, usually you pay money for your resources. So because of that, we have type checking in the system. So for instance, if I do this, which is a very common mistake, it turns out, you are going to get an error. So there's a lot of gobbledygook here, but basically here it says that that, hey, I'm expecting a key value pair. There is more to this. We have a system of type hinting. You can actually aid the framework. You can be more specific about, so you can have your own optional type system in there just to aid with this kind of situations in Python. But in this case, the way to fix it is to change return to yield. So this will turn parse record into a generator, and then basically it can be used as an iterator. So now suddenly everything is going to become correct again. All right. So one more thing before we go to BigQuery. I'm going to show you it's pretty boilerplate code, but if you ever play with this, you're going to hit this. Let's take command line parameters instead of this hard-coded data in and data out. So the way you do that, kind of the idiomatic way, is to use the rparse standard module. So let's say I want an input argument. And an output one. And a few more boilerplate codes. By the way, this part with argument parsing was early pain point with customers playing with this stuff. It was kind of difficult to introduce your arguments into the pipeline. All right, so we used these two modules. Okay, so what we achieved is that now we can write these beautiful command line parameters. All right. So the reason we did that, we're gonna need, when we're not gonna submit to the cluster, we're gonna need these input parameters. And since it was such a painful for previous customers, now if you use it, you saw it once, at least how to write this boilerplate argument parsing thing. So BigQuery source now. So instead of writing to a sync, now we're gonna write to a BigQuery sync instead of a text sync. A BigQuery sync takes several parameters, but at the minimum it will take a table. And if the table does not exist, it's going to require a schema also. So in this case, the schema, we're playing with this product ID price. So let's say we want a schema that has a field product ID that's type integer and a value field that's type float. So that's one thing, one modification. The other thing that needs to be modified is that BigQuery Sync expects, so the P collection, that's the input of the BigQuery Sync, is supposed to be, each element is a dictionary describing a row. So this is not what we get out of combine per key. Out of combine per key, we get key value pairs. So we're going to need to write a little transform function, transform operation. So we're going to use our friend map for that. And this time we're going to define on the spot the function using a lambda function. So what we get on the input, we're going to get a product ID and a value or a price. And what we want to return is dictionaries. Something like that. So now the adapting between combine per key and the write sync is done. One other thing, so we're going to run this in the cloud now. You can also run it locally. We support that, but I'm going to skip that step. We're going to run it in the cloud. One thing that it's useful when you run it in the cloud, we should probably make it easier. Basically, you need to enable logging at a certain level. Otherwise, you will not see a bunch of debug output that happens when you run from the command line. So yeah, especially if you are playing with your pipeline and you want to see what's going on, you will need this stuff. All right. So now this is ready. This is the final thing. This is how you run it. So when you run it in the cluster, you are going to have to add more parameters. It's not going to be as easy as Python current.py. but not by much. So, and in particular, there aren't that many knobs. So first you need to specify a project, which is a Google Cloud project. It's something that, you go to Google and you just define your own project. If you use BigQuery, you need to put also your credit card. Other projects are more starter, where you can just go for free. It's not, I mean, actually, it's I don't want to talk about prices, but yeah. You need to specify a job name, whatever you want. You need to call it something. I'm changing the runner, so this is one thing where that argument parsing thing helped, because now we're using, instead of using the direct pipeline runner, we use the blocking Dataflow pipeline runner, which is the one that is gonna submit the job to the Google cluster. And I'm gonna tell you more while this is running in after I launch it, about what's happening. But basically the only knob right now, it's the number of workers. There is a product that's not enabled for Python in part of the Google Cloud Dataflow, where you don't need even the num workers. We auto scale based on your throughput and things like that. But right now, for Python, you need to specify the number of workers. So this is gonna run with 10 VM instances in the cloud, crunching data. And then the other things are basically the input now is a Google Cloud storage file, which is exactly the same file that we play with locally. Output is a BigQuery table. And then you need to specify some Google Cloud storage staging and temporary locations where there all sorts of pipeline artifacts are going to be placed, like temporary files and things that need to be staged. So this is gonna start running in. So actually, what happens now while this is running? So this is gonna start outputting all sorts of debug messages about things. So it connected to the service, it starts doing things. So what happens here is, so we have a description of the processing graph. Then we issued a p.run, which invokes this Dataflow runner this time. What this runner does is not going to run anything locally. What it's going to do is going to create a JSON description of the entire computation and describing the whole graph, including things like, oh, there are some custom functions in there. What do I do with them? I need to serialize them somehow, put them somewhere so that they get picked up in the workers, because I'm going to run all this custom code in VM instances in the cluster. Nothing is run locally. So all this stuff is done by the Dataflow runner. So it submits to the service this JSON description of the computation, plus a bunch of artifacts with serialized functions that they need to be run in the cloud. And then it lets the Google Cloud Dataflow service that received this to orchestrate the whole execution of the graph. So locally, if you look, because it's all in GitHub, if you look at what runs locally, is basically the local runner is gonna do a topological traversal of the graph and execute all the nodes. But in the cloud, there is a full service that orchestrates these things. And in particular, it does very clever optimizations. So for example, like the trivial one would be to avoid putting stuff to disk until it's absolutely necessary. So for example, if you have, let's say, 3 parallel do's in a row. So a naive way to do it would be, oh, okay, so I'm gonna have to run first part do. I'm gonna get through all the P collections and I'm gonna put them to disk into an intermediate file or a bunch of files. And then I'm gonna start the second part do and read it from the file. And so this doesn't happen. Actually, all the part do's that are in a chain are going to be fused together and executed together. So there are a bunch of optimizations like that that make it much more performant, because if you avoid disk I/O, that will make it more performant. So now. We can look at the Google Cloud Console to look at our project. So for the ones that are running in the Google Cloud, you can you have a monitoring UI. So this is the one that's running right now. It's almost done. So it marked the last step the write succeeded. So it's going to take a little bit more time to actually finish completely, because the orchestrator, that's the Google service, also needs to start VMs, stop VMs. So now at this point, probably it's stopping, closing down all the VMs that did the computation. So you have this graph. One thing that I want to show you, because I'm pretty sure if you play with this, you're going to have to debug it. So we have worker logs. So for example, each worker logs a bunch of things about what's been processing, what's going on there. There's a bunch of, there's a worker startup log. These are the two most where you're going to spend your time if you play this. So worker startup is actually the one that starts the VMs executing the Python code. So there is a bunch of package installs in there that can fail. So if you have to debug that, you're going to have to look here. So let's see. So this is done. At this point, it's finished. And pretty much that's it, actually. Yeah. Oh, sorry, no. I want to show you that actually it worked. So, so I'm going to look at there's a BigQuery Cloud Console. And if you remember, Silvius C demo is the table that I was creating. And it actually created the same values. It's the product IDs and the values. So here you go, proof that it actually works. So yeah, that's a final thing.